Hello, everyone. I'm Chintu. I'm currently working with Christoph Steinbeck team here at FSU INA based in Germany. Today, I'll be presenting some of our analysis, software developments, and also potentially challenges that we are currently facing towards implementation of ontologies and their applications within data repositories and ELN that we are currently working on. So before I get into the specifics, I would like to present some of the examples of how data reported, especially within the domain of NMR, could have been better quality or like standardized by using control vocabulary or ontologies. Here is a classic example that we often present in our presentations where instrument names that are reported in the publicly deposited NMR datasets are not standardized. Here you have 8 ways of representing the same Bruker instrument where some of them have Bruker Evans 3 or LLL reported, basically difference in the fonts that software developers use in their application development, but all this could have been avoided by using control vocabulary or ontologies there. Moving on with an example on the solvents, sometimes these solvents are reported with or without concentrations, and also the concentrations are expressed in different formats. And also here in the bottom, you can see the example where the temperature is reported using different metrics there. Kelvins, degrees Celsius, sometimes hard-coded with free text or sometimes with degree C and things like that. All these could have been much more better represented and made more machine readable if it had been driven through ontologies there. To understand how ontologies are currently being used in repositories and ELNs, basically not specific to NFDI FairSpec, but in general throughout the NMR domain, we have gone through different repositories, and here is an example where Metabolites is the one where ontologies are most widely used in order to annotate the metadata within NMR domain. But within metabolites, we have found a lot of inconsistencies in terms of how the ontologies are assigned. Examples would be like the wrong annotation sources where a right annotation source could have been chosen if there is a proper system in place. And also sometimes broken links from the ontologies or the term accessions where things could have been corrected if we have gone through already assigned ontologies retrospectively. We are particularly interested in NMR specific ontologies that are used. So we looked at like what are the different ontologies that are used within the NMR domain. And within metabolites, we have realized that OB is the most widely reported ontology terms within the different data sets that they have. And very little use of domain specific ontologies or the control vocabulary have been observed there. With regards to CheMotion, CheMotion currently uses ontologies only to drive the choice of the templates that people use in order to choose the sample types. Beyond that, there are several areas where ontology could have been used in order to standardize the way the metadata is reported. Here in this case, this is a sample template where things are free text at the moment, but it could have been a lot more domain focused by using ontologies and driving the inputs based on the ontologies there. From yesterday's talks, you might have already realized that the current landscape of ontologies within the chemistry domain is quite promising. However, the original source of data or where the annotations are actually happening seems to be a bit lagging in terms of developments. So here at NFDI FairSpec, we are trying to develop or build software components, especially as a part of NM Archive project, where we are trying to build different web interfaces wherein the input fields are more ontology driven, and then the components can be used across different applications without having to redevelop again. So I'll be presenting some of the developments that we are currently working on. Feel free to get in touch with us if you are interested or would like to provide your feedback and comments on how we drive this forward. One of the primary focused ontology component that we are currently working on is similar to what you might have already observed in case of Google Gmail. Smart Compose, where you type in certain text and then there is this auto suggestions from Google. So similarly, we are working on a Smart Compose component, which is ontologies or control vocabulary driven. where the user, when they start typing, there will be auto suggestions based on ontology linked behind the scenes based on the context, and also sometimes the controlled vocabulary. Here in this case, when the user starts typing BRV, actually the machine learning algorithm behind the scenes actually realizes that this could be an instrument name and be able to suggest few suggestions based on the controlled vocabulary, or in some cases the ontology there. In short, the user still continues to use the interface as if he's inputting raw text, but behind the scenes, the system is able to annotate this information and then be able to export this information with all the rich ontology annotations that the machine learning can potentially read at some point. Here is another example where the solvent is being suggested there. Another example is with regards to the input field, where user, when they start typing, they could still have the free text, and then the suggestions are populated based on ontologies. And if the ontology term is not defined, then potentially an option to request a new term or submit a new term could be submitted at the same time. One of the challenges that we have come across is with regards to data that has already been deposited across different resources. So retrospectively going back to the data that has already been deposited, in order to annotate that data, that could be challenging because there is a lot of human curation needed. So in this case, one of the components that we are working is to be able to auto-annotate text blobs based on machine learning, and then checking with the users if they are happy to go ahead and approve this, or if they have any alternative suggestions. And this suggestions or the input from the user is then backfed into the machine learning models so that there is an active learning happening in the loop, so that the machine learning models become better and better as we go ahead. This is slightly better with domain-specific ontologies, as we already know the context or the specific areas that the input is given from, and also the user doesn't have to input any, have to constantly spend a lot of time in order to provide this feedback. It should be totally intuitive and easy to use with few clicks. Quick overview on like different ontologies that NMArchive we are currently planning to use within this. So NMR specific ontologies or the controlled vocabulary here, and then the chemistry related ontologies, biological. I don't want to get into the details of this, but these ontologies will in turn have precedence in terms of what suggestions we give, and based on the context or the domain where the input is being fed back. It's not just the ontology capture that we are currently working on. We would also like to export the data with respect to ontology annotations. So as Stephen earlier mentioned, bioschemas is one of the areas that we are currently working on, but behind the scenes, persistence layer on the database has this information stored in the form of ISA schemas. If you need more information, the link is provided here. Basically, ISA provides a nice key value pairs where you could represent the ontology with different annotation values, source, accession, and other things there. As I mentioned, here is an example where chemical role is being exported for a molecular entity, and then the respective details are provided based on in compliance with the bioschemas. This is still in development, but currently we have working prototype and few API endpoints if you would like to try out a few. So finally, I would like to briefly touch upon the challenges that we are currently facing. So as a repository developer, we are currently working on automating the entire process of data deposition, but that requires a lot of assumptions, and at the same time the input fields or the properties that are provided or automatically extracted are lacking the context. In this case, on the right side you see the example where we have extracted some of the properties from the Bruker output, but they all lack specific details about the units and also the different values. And once you have different instruments and different data types, being able to make this data coherent across different sources is going to be quite challenging. And also we want to make this as easy for the depositor as possible. But however, with this sort of information being submitted from the instrument data is quite challenging for us to deal with at a later stage. Retrospective annotations, as I mentioned earlier, if we have information that is already submitted, there is a lot of human curation that is required in order to annotate the data that is already there in the public domain. And also, there are challenges with regards to validating these auto-annotated text using machine learning models, and also how we backtrace this in order to train new data sets. ELNs and repositories will serve as a good source of reporting missing ontology terms. However, these ontology-rich components have certain limitations on how we can submit new terms, and also the process involved in acceptance of these terms and back communicating with the original source of information about the new missing term that has been added is going to be quite challenging. And also we were trying to make this process as seamless as possible, wherein new terms can be submitted directly from ELNs and repositories, but without actually compromising on the user experience there. So wherein proper training has to be given in order to data submitters to be able to produce this data in a seamless way from the source of information. So that's all from my talk today, but if you are interested, or if you have any nice ideas or feedback, or if you would like to check out what we are doing, here are the links. The NM archive is currently beta stage, and some of the components that we are developing are still in early alpha phase. So if you want to drive the direction in which we would like to evolve this, please do reach out to us. Happy to answer any questions that you may have.
Very good. Okay. Thank you for the invitation to talk a little bit about our project. This is IUPAC project on the development of a standard for fair data management of spectroscopic data in chemistry. And we have been working for some time on this. For those of you who are not familiar with this project, it's a IUPAC project to develop standards for the production and dissemination of digital data objects that contain enough spectral data and metadata that they can be findable, accessible, interoperable, and readable, and essentially fair. And particularly in the readable, we wanted this to be both machine and human readable. Now, after much discussion, we've decided that the contribution we can make in this area has to do with collections. That rather than focusing on the minutia of the data set coming out of the instrument, for example, what we're really interested in is seeing a domain-specific recognition that when data is published, when data is produced by ELNs, for example, there's a real context associated with that that's associated with other spectra, with other compounds. And it's really that connection which we're trying to capture here as what we're calling a fair data collection. And the way we envision doing that is through something we call the fair data finding aid. If you're not familiar with the term finding aid, that comes from the digital archiving, sort of the library museum sort of area. And we think it's very useful here as a concept. The idea basically is that instruments or ELNs or publications can produce collections of data that need to be discovered. And the problem we have, as we've discussed before, is that when we have had this happen so far, we have supporting information in the form of PDF files, which is perhaps human searchable to a certain extent, but is certainly not machine readable. And so our idea is to create an organized collection from whatever comes to us from these various sources. And that conceptually becomes a IUPAC Fair Data collection, which has IUPAC Fair Data objects. Now, these aren't quite the objects that we think of in terms of digital objects, because these are more conceptual objects, but what other people would call digital objects would be what we're going to call digital representations, and I'll talk about that in a minute. And the process of making this IFD collection from some sort of input of data normalizes it in the sense that we make sure that certain file categorizations are obeyed, that we have very domain and subdomain specific metadata. We have the data and the metadata objects, and we have a reasonably clear separation of those two. We believe very strongly that we need to have multiple representations. So for example, in a NMR spectrum, the actual FID is one of the key representations, but there are many other representations. For example, just an image is sometimes the valuable part for some people, or various other data formats that allow for different types of interaction, reuse of that data. We want to make the critical associations between the spectra and the compounds, the structures that are there in that collection. We plan to have this able to be almost entirely digitally curated. So if we do this right, people can have data in various formats, and then it can be piped into this sort of collection automatically. And this will provide for something that we've never had in chemistry, which is a validation service in principle, not for the ontology, but for the actual data. Does this compound correspond, for example, to this spectrum? What's the likelihood that this really is the compound? I think that gets to some of what David Wizard was talking about previously. Okay, so the essence of a collection is that we have structures, we have spectral data sets. It's a one-to-many, many-to-many kind of interaction. There's a lot of flexibility here. And then also with these, we have a sort of an analysis aspect, which connects those as well. So the key here is what I want to discuss is the idea of a finding aid. And this is a digital object that describes the collection's representations in a machine actionable manner, including the properties and associations. And what you're going to see here is nothing. There's no ontology because we're not there yet. So one of the reasons I'm here is to find out how we can get there, or if we need to get there. And I'm learning things all the time here these days. But in any case, right now, it looks like this. Basically, we have a JSON serialization of this finding aid. The finding aid is self-descriptive in terms of its format and its standards relative to our presentations. You can notice that there's a very hierarchical sort of Java-like description of all of these components. That's because the implementation, the reference implementation is written in Java, so it has classes, subclasses, fields, methods, and such. And so there's a lot of sort of built-in ontology that's not actually expressed as an ontology, but there's a lot of structure to this whole concept. And you can see that the collection itself, this particular one, has 3 collections. It has a sample collection, a spectral collection, and a sample spectra association collection in it. Just to go through the basics of where we're at right now with the finding aid, there's basically a header section that will describe exactly what we're looking at. One of the important aspects of this is it's subclassable. So for example, this is a IUPAC Fair Data collection, but we also know it's a IUPAC FairSpec finding aid, which has a very specific subclass aspect to this data finding aid itself. Where it's corrected, we have contents, citations, resources, and the collection set is the key area that has the information. So looking at the contents, we can find out what kind of collections, sub-collections we have within this collection in very clear specification of based on classes of the fair data. We have properties, which is where we would get into some of the things that that Shandu was just talking about in terms of key value pairs that relate to any object in this collection. A collection set then has the actual collections. And here you can see we've keyed in on one of the NMR spectral collections, and this is where Chandu's work hopefully will come through, and we can give us some structured mapping into ontologies for some of these terms in terms of properties. There's also representations, and so this is where we get into the idea that you can have a zip file that would be a Brooker directory, but you could also have a PDF that has an image in there. This is quite possible, a PNG image, NMRE data file, etc. And we allow for parameters, and what we mean by parameters essentially right now is free format, in the sense that we are not going to specify what the form of these parameters is, but someone like Chandu could, and be more specific in terms of what is allowed and what are the units, etc., of these various parameters. The difference between the property and the parameters is that the properties are the ones that we feel basically need to bubble up into this finding aid so that these can be found within the collection. Again, we're focusing on the collection itself as opposed to individual broken out data sets. So just quickly, we're trying to get the discipline specific aspect here. It's a highly structured collection of collections. It's extendable systematically, and it's class-based object-oriented description, which should be amenable to ontology descriptions. It consists of many key structured values. Items have properties, items have parameters, and we think it's generally applicable to any domain, not just chemistry. The whole idea of the collection of data is where we're at here. So there it is. Kind of fits. This is our overall schema in terms of how it would fit together with ELNs and publications and such. We see it as something that could be valuable all along the way from the beginning of data creation and on. We hope others will join us in our endeavor and help us design this further. Questions relevant to this discussion: how can we best integrate ontologies into this scheme, and how is the best way to serialize these finding aids to maximize their findability? And it's a very flexible system, so I'm really interested to see how ontologies would even work for a system that's so open as this. Anyway, here are some links. When you get these slides, I'll have probably a few more links. We've published a paper on our principles. Our next paper is going to come out on the actual formats of some of this. So I'll stop there. That's all I wanted to say to get people started and thinking.
Excellent.
Can you hear me okay?
Yes.
Good, good. Well, thank you so much for inviting me to come speak today, and I hope that my voice will hold up. I'm a little under the weather, not COVID. School started back up, and I got my little one here who's also a little sick, so if he starts to photobomb, you'll understand why. So today I'll talk to you about ontologies, Thesauri, terminologies. We're also using taxonomies of various types inside Pubchem. We use them really quite extensively and everywhere. And so this is more or less I would say a very brief introduction of an introduction in 7 minutes. So to give you some idea where we're coming from, we find these extremely useful. We find that having sets of terms and their synonymy is really critical. Understanding the context of those terms is also extremely important for us. And our ability to understand the relationship of the context between things, as well as the similarity between them, is also super important for us. It's great if we understand the grouping and interrelationship in some hierarchy or category. And then in terms of computability, that's also a very desired feature. But I've kind of listed these in the order of utility from left to right, left being what I would say most useful for our users, versus those that are happening for or being used in other aspects of our system. But the other interesting aspect, at least from our perspective, is that the difficulty to implement and to create the sets of terms versus the other aspects of relationships between computability, it just gets, I would almost say, exponentially more difficult to do, to represent well, to do the data modeling, and so on, to make sure that you have a well-represented data set. So we are extensively using ontologies, terminologies, and so on in the context of our Pubchem RDF, which is a subset of Pubchem in terms of its machine readability. What you see is just some of the primary nodes that we have inside Pubchem. We first pushed this out about, what's it now, 7 years ago? And we're currently still in a beta form, but we're getting quite close to a 2.0 final. We have about 20 billion triples of core data with relationships that are displayed, plus we have the integration to other RDF collections, so it's interoperable in that fashion. Plus we still have a lot of legroom in terms of adding more and more of the content that we have inside Pubchem. About 100 billion of our triples are just chemical similarity pairs. And it's organized by layers of onion that you can actually use in various ways. And we provide a number of examples where you can load this data into your triple store or graph database, and you can answer some practical questions with the RDF content. But this is empowered in large part due to the ontologies that we use that allow that computability aspect to work. But we extensively use these terminology and other forms to allow us to represent data. So if you go to one of our protein or gene summary pages, if you go to our taxonomy pages and so on, these are organized using these terminology, Thesauri, at times ontologies, and so on. Allows us to group things and represent it. Here you see an example of xylene inside Pubchem, which doesn't have a discrete chemical structure. It's actually a mixture of 3 different entities. And you can now see records like this inside Pubchem, in part due to our use of terminologies that come from various types of curated and authoritative sources. But it really, we're building up the relationships between these entities and trying to build, especially into the RDF side, more of the computability aspects. We also use them quite extensively to try to summarize information. In this example, we're showing you our co-occurrence pages that we have for chemicals to other chemicals, chemicals to genes and proteins and enzymes, and chemicals to different types of diseases. We actually have these relationships in every direction. So we have those that go from disease to chemical, disease to disease to gene, protein, enzyme, and so on. Because oftentimes we have for a given record tens of thousands of papers, and we're trying to then group and summarize that data in some fashion. And so you can get a quick sense of what is this thing known for. Which really would not be possible unless we had extensive use of terminologies to allow this to be empowered. We have, in our own way, developed a number of control vocabularies, in part out of sheer necessity. We don't like to create these because they're always troublesome to create. In this example, you're seeing on the right-hand side are Pubchem compound table of contents as shown within our classification browser, just a snippet of it. And you then just see the expansion of the number of experimental properties that we have. We got to P before I had to cut it off. Inside our table of contents, just for compound alone, because we have separate table of contents for other entity types inside Pubchem, like enzymes, genes, proteins, pathways, patents, and so on. We have just for compounds alone over 500 different entities or types where we can then hang data off. The numbers that you see there to the right are the number of compounds that have this type of data. And so we're attempting to use various types of terminology, thesauri, and ontologies to pick good terms. Ideally, we would just use something authoritative like the IUPAC Gold Book, and then just say, use that term. If ChemI handle these things, we'd use those. We are using ChemInf and others to a certain extent and degree, but having a rigorous description of the many types of data that chemists use is not always a trivial task. But we also use terminologies, thesauri, ontologies, and so on to improve the quality inside Pubchem as a whole. We're literally using hundreds and hundreds of these terminologies within Pubchem from many different sources. Really, I think we're in the low thousands at this point. So we oftentimes have issues where we have cross-domain problems like MIPA, monoisopropylamine, which can be found within text and many other regards. And so it's quite well known that abbreviations are problematic, but even pure chemical names, where a chemical name could be part of a type of enzyme. That enzyme name itself may be part of a disease name, and so on, which makes it difficult at times to pull out and make sure that you have the proper representation of a particular term or entity. But there's also huge issues or problems that we have recognized in trying to use and apply these different sets of collections. They're oftentimes, they were built by some postdoc who's now moved on, and it's basically orphaned. Some of them are quite well organized, others not so good. We have a lot of applicability issues where the use case of the ontology is not the same as the use case of how you want to apply it. And that can create some huge issues where then you don't have really an authoritative or curated approach that's dealing with the types of use cases that you want to deal with. Oftentimes we notice there's a lot of assumptions in these that you're supposed to know that already to have certain domain knowledge to use them, and sort of that hidden data is often a problem. We've also noticed a number of things that have been claimed to be an ontology, but are maybe just a bag of terms with some crude relationships, or maybe even to the point of a taxonomy. And so really trying to get these to work well is problematic. So what I'm trying to help you to understand is that we use these for many, many, many purposes, primarily for machine readability, improving quality, analyzing text, but even well beyond that, to organize data, to try to create new pages that contain data from different types of collections in a way that makes sense to our users and doesn't cause more problems than it creates. All this, I want to just quick shout out to the Pubchem team, which through their hard work and dedication that we've been able to do much of what you see, but also to our many collaborators. So I'm happy for any questions you might.
Thanks, Stefan, for sharing this, and also thanks to Oliver and others for organizing. It's nice to be here virtually. So I'm to talk about ClassyFire and talk about how it grew up and how it's being applied, and then also some extensions for it. The original idea for ClassyFire came out of, I think, more a joke from a discussion with a graduate student, Yannick Jumbu Fernang, who some of you know, where they have some web pages showing some sort of comical structures of what they look like, whether some look like penguins and some look like giraffes or cats. And it led us to this idea that, maybe we could classify structures not so much by what they look like, but using the same taxonomy that we've historically used for animals and plants, and to structure that not only as a taxonomy, but also further as an ontology. So as it emerged from just the joke to something that was a little more realistic, We realized that there are some challenges in trying to classify chemicals by structure. This idea that there are already existing classification schemes. We classify amino acids and lipids according to certain schemes. Some are based on structure, some are based on biology, which makes it a little more challenging. We also had to come up with a preferred nomenclature because there actually were quite a number of common names or terms used for basically the same structures. Again, there's lots of discordance in the community. We had to create a clear, controlled vocabulary. We had to develop definitions. We had to develop well-defined categories that were structure related. And so that required a fair bit of work with various domain experts. And then we also had to realize that chemicals are often made up of components, some of them which are chimeric or hybrid, and how to deal with that in some sort of consistent and logical manner. So this is an example of sort of a complicated compound, valclavin, and essentially it's a beta-lactam or a lactam-like drug, but it's also a dipeptide. And within this particular structure, you can see all kinds of functional groups. You can see carboxylic acids, you can see alcohol or hydroxyl groups, you can see amines, you can see peptides or amino acids, and then you can see the beta-lactam or the clavam ring. And our decision was to basically try and identify the largest and to some extent the most complex functional group, and to use that as the way of identifying the direct parent. So in this example, there's actually two large groups, the clavam group and also a dipeptide group. Both have the same number of atoms. One is technically more complex, the clavam group, but in this case, this essentially has two direct parents. The schema for ClassyFire is essentially based on using JChem, the web services from ChemAxon, that does a lot of feature calculation, superstructure searching, but we've also generated by hand thousands of smiles, strings, and Marcouche patterns. And those were used, so the stuff in blue is sort of the external stuff, the stuff in gray is our own. And it's from those collection of properties and features and names and nomenclature from IUPAC, structure similarities, functional similarities, that allows us to identify, I guess, a class or perform a class assignment, then to rank them, and then to generate the taxonomy or the structure. And so this is an example where all compounds in ClassyFire are identified as chemical entities. They're separated into one of two categories, organic compounds and inorganic compounds. The organic compounds are separated into hundreds, actually thousands of other subgroups. The inorganic, I guess, is more hundreds. And each of those are structured into kingdoms and super kingdoms and classes and direct parents. It's too much to cover in 7 minutes, but the paper was described in 2016 and worked with several groups across North America and Europe to try and get some consensus in the ClassyFire schema. And then we developed a server, a web server, which has been around for about 5 years now. It allows people to upload anything from 1 to a million compounds at a time. It'll take an integer smile string. It generates classifications. If it's already been classified, it does a lookup. If it's a new compound, it takes about 4 to 5 seconds. We've tried to make it consistent with previous classification schemes that had been used by Kebi and Mesh and lipid maps. Right now, there's almost 5,000 compound classes with that controlled vocabulary and full text definitions. And we've been using it to classify all of the compounds up until about a year ago or two with Pubchem, with our own databases, HMDB, T3DB, Drug Bank. Pretty much all public chemicals are now classified through ClassyFire. We still get a few occasionally from things that we didn't know about that are novel and which ClassyFire will reclassify. This just illustrates how it looks, how people have pasted in a structure, converted to smiles and inchi. You can see the taxonomic classification, this kingdom and superclass, class, subclass, and then below that certain levels. In terms of the applications, the paper has been cited about 500 times, so it's getting a lot of use. We originally developed in the area of metabolomics, but people are using it in many other areas, natural product chemistry and others. And it's being used to try primarily cluster or group compound classes when people are talking about them in papers. We're using, and I think others are using, the classifier definitions, the control vocabulary, to auto-generate or auto-calculate compound descriptions or to create definitions for compounds. We've been doing that for, again, a number of databases internally and externally. People have also used ClassyFire as a way of identifying compound classes via mass spec or NMR. So if you have an unknown and you've got some compound spectrum for it, sometimes it's very hard to identify the exact compound, but you can train to identify that it belongs to a certain class, that it's a member of the amino acids or the alpha amino acids, or it's a member of the lactams. And so that's been used in a number of tools developed by some of the folks here on today's call. We also use it, others use it as a way of filtering out compounds, to say that we know that certain classes of compounds have very distinct collision cross-section area, or others have a very distinct retention index, others will have a very distinct mass spec or NMR set of chemical shifts. And so that allows you to train or adapt your predictors or calculators to specific classes of compounds. It also is being used to accelerate chemical similarity searches. And then there's lots of other applications that we've seen relating to cheminformatics and machine learning. So it took off in unexpected ways, and I think that's a neat example of how a good or useful ontology can be used in lots of unexpected ways. Over the next year, we're updating ClassyFire version 2. Hope to release in early 2023. We'll formalize it with an OWL and create an ontology viewer. We are also writing ourselves out of JChem so that it can be a standalone server, so it can be downloaded and people can run it locally if they wish. One of the biggest challenges is to write a structured to IUPAC name converter. All of those are commercial. So we've had to spend the last year or two reading through the IUPAC book and converting everything. This will make it about 2 to 3 times faster. We're adding about 200 new chemical classes and some minor fixes. And then we've been integrating it into another ontology that we've been presenting periodically called ChemFont, for the chemical functional ontology. So this is an extension which is just not a structural ontology, but more a function ontology to try and connect chemicals to biology. And so we wanted to try and get information about their applications in biochemistry, medicine, environmental science, food science. We wanted to get things related to physiological effects, their disposition, their roles and processes. And we've used a lot of the data that was built from our own sort of hand-curated databases, HMDB, DrugBank, T3DB, but also some of the ChemInf ontology and others from KEBI and EPA and the NCBI Thesaurus. Right now, the ontology ChemFont has about 73,000 defined terms, and we've classified about 260,000 chemicals. There's a website. It's still evolving a little bit, although it's close to its final version. And it's mature enough so that we can start using it for creating some interesting knowledge graphs. This is an example of tryptophan, and it's showing how and where it can come from, how it's associated with certain diseases, how it's transformed into various indole derivatives, which microbes are responsible for that, and then again, some of the side effects that these things have. So it's connected or connectable, and the idea is to make it informative, machine readable, findable, fair, compliant, and computable. A lot of people have been involved in it for a lot of years. These are people who played probably the most significant roles, but I could easily make this into 3 or 4 slides for people who contributed to it. And so that's a quick summary of our work.